All right, thank you so much for the introduction. It's so exciting being here. This is, after all, these are my roots. You know, I started back in the 90s, the glorious 90s. So I really thrive, and I feel like, back home. So I wanted to talk to you about trustworthy AI, but not in a traditional way. So trustworthy AI now encompasses many different properties that we're seeking for, like ethics, fairness, robustness. And usually, we tend to see these things in the concept of computer visions or maybe now in natural language. So I wanted to give a different twist and talk about system security because those are my roots. I started off by reading Frack, Smash the Stacking for Finding Profits, IP spoofing, demystified, those kind of low-level memory corruption vulnerabilities, exploitation techniques. So I am a system security guy, and I work at the intersection of program analysis and machine learning. And this is where I want to talk to you about machine learning in this context. So we can start off by saying that no day goes by without reading machine learning fantastic advances nowadays, right? I'm sure that you can read in almost every day's issue on the newslet about advances. And this is the only moment where I'll be mentioning large language models, I guess. But to summarize the exciting period that we are witnessing nowadays. And we have reached what people call, the research community calls superhuman performance in several tasks. So if you look at image classification, so there are models that actually perform better than humans in recognizing images. And I'm not talking about recognizing between a dog and a cat, but recognizing different breeds of dogs and cats. And I have a bet that if I ask random people, including myself, whether I recognize between two different breeds, I would probably fail. So the question is, what about security, right? Is this a new opportunity for us, or have we been doing this for a little while? So actually, we've been doing machine learning in security context for a long time. I guess the first academic paper dates back around the late 80s by Dennings, talking about network intrusion detection systems. The point is that back then, we didn't really talk about machine learning. We really talked about very simple statistical models, very simple statistical learning systems. And it's only nowadays that we really use the term machine learning, or even more, AI, right? Because it's streamlined and a little bit hyped. But the question is, we've been doing research on this for 40 years. So we kind of, if you look at research papers in academic community, you can see that pretty much all the models apply to any sort of problem you can think of, whether it is window malware classifiers or PDF malware identifications, attributions, so forth and so on. They all achieve 99% F1 score, which is a metric that tells you how good you are, basically. If that's the true answer, then I would say that the problem is solved, right? So I guess that there is a little bit more nuance than that. And maybe the conditions are not there yet. And I'll try to advocate and argue why I believe the conditions are not there yet, and what are the problems that we really, as a community, and my hat is more like the academic community, but there is an intersection between academia and industry, so where we should be actually working on. So I guess now the next slide is more my homage to RomHack. And so machine learning, we can claim that machine learning already solved many problems in computer security, right? And this is my homage to RomHack theme this year. So actually, not. Okay, so this is what Mario says, not really. So let's try to understand why. There is one thing that I feel sets machine learning apart from different other domains, like whether you look at computer vision, whether you look at natural language, for which machine learning is really thriving. Security has a peculiarity. But before getting into this, buckle up for a second, because I wanted to summarize 40 years of research in malware analysis and detection, just with a few highlights on how we got here, okay? And I am not really stealing, but taking these few next slides from a recent keynote, so you get a keynote in the keynote, from Davide Balzarotti that gave a keynote at Coda Spies as an academic conference. So fast forward, we started by creating manual signature exploiting domain knowledge. So we look in computer viruses, looking at specific patterns in which the virus would infect another piece of software. So we'll actually identify sequence of bytes that would identify a useful pattern to identify viruses. And fast forward, we learned that actually we can automate this process by creating an algorithm that actually can generate these signatures automatically. But then also we ask ourselves, oh, hang on a minute, we can actually write now attacks that blend in the normal malicious traffic. So if the signatures are not representative of semantics, and I'm going to be using semantics a lot in the talk. Semantics has a very specific meaning in computer science, so loosen up a little bit. So think about actions of interest or indicator of compromise or behaviors, what you care really about the malicious piece of software you're looking at. So if the signature doesn't really match for that, you leave room for attackers to create legitimate-looking signatures, but still carrying out the malicious behavior. So then the community say, oh, hang on a minute, okay, this is not going anywhere. So we should focus on behavior. We should focus on identifying semantics. We should focus on trying to identify what is it that really carries out the malicious behavior in a specific piece of software. So there has been a pivoting point back in 2005 where people started to propose template of semantic behaviors. So this is very cool. The problem is that it's a little bit abstract because you can realize a behavior and action in many different ways. And that's the real problem. So until we're able to capture this specific component, we always leave rooms for attackers to manipulate. And the big point in this paper is also templates had to be manually specified. So there's still a lot of domain knowledge to understand, okay, what is this behavior that you care about, okay? You can think about very complex behaviors, right? So there is a point after which people started trying everything and say, oh, we should be looking at a sequence of opcodes in the binary and then build some n-grams, like, sequence of consecutive bytes that represent instructions of interest and then, build a model out of that. No. Let's have a look at APIs that are actually executed by a binary or analyzed statically, that may be executed by a binary. Oh, no. Let's have a look at Windows native API, or let's have a look at system calls, because that's really the interaction that a process can have with the system. So that's the true manifestation of behavior. Well, that's not correct. Let's actually build complex dependency graphs, so you can represent a piece of software with different graphs that captures different properties, control flow properties, data flow properties, and so forth and so on. So we end up by trying everything on everything, and we end up by having similar results, facing the same challenges, that models can always be bypassed, and there is no clear solution. So this ended up in a bunch of papers being published and real no advance of the state of the art. I'm exaggerating a little bit. There's always a lessons learned, but this is actually the situation. Then we started to say, okay, now we have a bit of better knowledge, and let's try, however, to use machine learning. So the process that we follow was like, domain knowledge, manual signature identification, automated analysis, and we started to with more and more data. So this is what machine learning really thrives, because it's a data-driven approach. Let's use machine learning to learn patterns of interest. And we started blindly applying a bunch of models on binaries, on system calls, on graphs, and so forth and so on. Keeping in mind also that back in the days, there was no effective ways to also learn embeddings, so to map a complex graph, for instance, into a numerical feature space, a numerical vector that is useful for machine learning. So there's been a lot of approaches even there. But it's not clear because everyone gives the same results. In a sense, if you try on a benchmarking data set, they always give 99% F1 score. So there's something missing there because when you try in real life, everything is broken. And here as well, machine learning researcher tries to do everything. Like, let's try, Bayes network, linear SVM, RBF SVM. Oh, no, now it's very cool. Let's try deep learning, right? Convolutional neural network. Let's try transformer, which is at the core of large language models. All these things learn suitable representations of the data that you provide them. But the question is this the right representation? What are the properties that you try to capture with this? Because if you don't capture the right properties, you always leave room for manipulations. and for attackers to actually bypass the systems. And actually, this is where we entered this dark age of machine learning and malware analysis and detection. And I feel that despite all the best effort in academia and industry, we're still quite here. So we still don't know what are the real important things that we should be focusing on. And the reason that I wanted to mention is because there's one peculiarity of security that sets it apart from other domains. Security is inherently adversarial. And this is a thing that we can't just, factor out. When the reason about these things, we have always to think about adversaries. What adversaries can induce, there are different consequences. So, for instance, when you deploy a new detection system, adversaries will try actually to bypass it. That's, the old cat and mouse game, right? So it's always there. But if you look more specifically at how this translates into machine learning, what you actually end up by observing is what is known as a distribution shift, okay? So now, let's set aside for a second, and if you guys have ever had classes in statistics and probability, this is not a class of statistics and probability, so don't get alarmed. But I'm assuming that you would have always gotten at the very beginning, let's assume that data is IID, EED, right? And we always took it for granted, which is identically and independent and identically distributed data. We always took it for granted when you do, that exercise in statistics and probability. Say, it's assuming I don't know what it is really, But this is the core. This is really how machine learning works. For the sake of the talk, I'm going to refer to supervised machine learning, so classification, where you have a classifier, you have a labeled data set. The assumption here is that the data that you use to train your classifier, the source that generates this data, programs that you observe, the programs are independent from each other. That's the assumption. So there's no relation between these programs. And also, in this point, we don't really know, but let's assume that this is holds. But the other assumption is that the data that you observe at test time should be drawn from the same distribution that you train your classifier with at training time. So machine learning is not a magical toolbox. It's not a clairvoyant toolbox. It's just maths. It's just statistics. And if this assumption holds, then machine learning works. But in security, this doesn't work because you observe new threats over time. You observe attackers that try to manipulate the system to break the system and expose differences in behaviors than the one that you were able to capture earlier. And there is also here a peculiarity. You remember that I mentioned several times representation, so how we represent objects of interest. So we have a binary, and we have to translate a complex binary or execution traces in a vector of numbers. So this process is usually lossy, so you lose information. And the more information you lose, the more room you leave to attackers for manipulation, because the more the representation of this object is imprecise or is approximate, the more you might observe at test time distribution shift, not because you're really observing something new, but because what you try to model is wrong or imprecise, okay? And so far, there is a little bit of an open problem. So just to give you an analogy, in computer vision, now the community says that what a convolutional neural network learns is useful for what we want to do. So a convolutional neural network learns what is known as a translation equivariant representation, big words. So if I have a bottle and there is a black screen here, I learn a representation. So I translate, there is a convolutional operator on this image, and I learn a numerical vector, so a vector with features and some numbers that represent this image. If I shift the bottle on the right, I learn a representation and a translation equivariance. So the representation that I learn about this image is not completely different. It's just similar to the previous representation. Because I want to capture the fact that these two images are actually similar. There's only the bottle that's shifted in the background of the image, right? So when you apply the same approach to binaries, what does it mean to learn something that shifts? Like it's unclear, right? What is the goal? So maybe there are other properties of binaries that we need to capture. And this is an open research problem. So the main problem is that this rule is often violated. And when this is violated, everything is broken. So what I believe we need really is to understand and improve the effectiveness of machine learning approaches for system security. So in this context, because otherwise it's very broad, in the presence of adversaries. So we shouldn't really factor adversaries out. And a key point in all of this is how we learn a suitable representation of the objects that we care about. Programs, documents, and so forth. How do we learn something that captures properties that represent semantics, what I care about these objects, right? Because the more I am far away from this modeling, the more this semantic gap is greater, and the more I leave room for attackers for manipulation, and the more my system will be broken. The effectiveness of machine learning system, therefore, in this context, is really intertwined with the underlying abstraction, the program analysis that I use to extract this piece of information, and how then I represent this from a program analysis perspective into a machine learning model. And this affects robustness to distribution shift that I mentioned earlier, explainability, performance on clean data, costs, and so forth and so on. This is a big, big problem that we need to solve. And disclaimer and spoiler alert, I'm not going to be solving this in this keynote. So several of these problems are just open. But I feel like I really wanted to leave you with a bigger picture and say, okay, this is what we should really be focusing on. And the question is trustworthy AI for system security possible? Well, usually headlines like this have an implicit no as an answer, but I guess there is a plan, and at least we are aware of some of the issues that we have at the moment. So to set the scene now, I'm going to be talking just about one problem. So adversarial machine learning, but in the context of software. So not computer vision, but adversarial machine learning on binaries, on programs. And I'm trying to understand, what are the differences and whether there are analogies, whether the problem is easier and whether it is not. And I really like the slide that Gerardo, I guess, mentioned earlier, this pie chart that show the dichotomy between attackers and defenders. So this is an attacker perspective, but we're going to see how and whether this is useful for defense's opportunity as well. Okay? A spoiler alert: the problem is challenging. So there is no clear solution yet. But to set the scene, okay, let's imagine a dystopian future. Like we didn't have enough problems with COVID, with war, and with anything that's happening in the world. But something even worse where panda are just forbidden to roam around. Panda is so cute, right? And imagine just a city where you have surveillance systems that are powered by machine learning surveillance systems where panda are just forbidden because they are too cute, okay? And that's reality. So one thing that we don't know is that panda spend a lot of time chewing on bamboo sticks, right? Because it's a very low energy source, so they need to chew a lot, to get a lot of energy. So they have a lot of time to think about it. And one thing that we don't know is that panda are fluent in math. Okay, this is part of the storyline, okay? So I'm not sure whether it's true, but I want to believe that. So, and they remember that there is a seminal paper, it was called Intriguing Properties of Neural Networks. This was published in 2013, I believe. And this is where actually it started off the whole field of adversarial machine learning, which is crazy, okay? By the way, I mentioned that I would mention LLMs only once. It's not true. So we have adversarial machine learning attacks on LLMs as well. The problem is the same. It's even exacerbated on LLMs. So we can call it adversarial prompting, which is slightly different, but the reasoning is the same. So how does the attack work? So to give you the intuition, so a panda sees on the paper, oh, well, there's a picture of a panda, so the panda understands this very well. And the idea is that you create an adversarial mask, so of noise, so this part in the middle is noise, that once it is added to the original image, you obtain an image that is legitimately looking as a panda. So from a human being perspective, this is still recognized as a panda. So this noise is not actually random noise, but it's noise that is optimized to be added on this image so that the resulting image is still perceived as a panda. So the semantics for human beings are preserved. This is an important point. But actually, the system misclassifies this image as a gibbon with high confidence. And of course, gibbon is an example. You can actually misclassify this with the target class that you want to in the system, okay? So the panda says, oh, this is pretty cool. So let me just go, but this is on pictures. Like, this is a digital artifact. So the panda says, well, I need actually to carry out this attack on surveillance systems in the physical world. So I need to think about realizable attacks. So the panda says, oh, cool. Let me just go to a costume shop. So the panda goes to a costume shop and it doesn't find this optimal noise, okay? Because this optimal noise might just exist in the digital world. So in the physical world, it doesn't exist. You can't really print it out. There is a different gamut of colors. It doesn't really exist. So you have to set up for something that is approximate. And the Panda says, cool, there's a picture, there's a mask of a fox. I'm gonna go with that. So I'll just, wear this fox mask, and I am good to go. Because now when I go around in my city, I would be classified, according to this adversarial tag, as a fox. The truth is a little bit more grim for the Panda, because there are several artifacts, several problem space constraints that the Panda hasn't satisfied in the real world that give away the fact that the Panda is still a Panda. The panda paws, the black and white fur, the big chubby belly, and so forth and so on. So, sorry, still denied. Banned outside the city. So let's try to understand a little bit better what happened. So we start off with an image of our artifact. We learn X, which is our vector that represents this image. How we learn this doesn't matter, so we can use it. Nowadays, we use a neural network, ResNet, the CNN, the convolutional neural network. But it doesn't matter. We can learn, actually specify, like in the good old days, like some features where each dimension in the vector represent one characteristic of the image that we care about. But nowadays, it seems that learned representations are much more effective than that. So the gist is that you take an image, you learn a numerical vector representation of this image, then you craft this adversarial noise, you add it, and then you end up with an adversarial image, whose corresponding adversarial representation is x plus delta, okay? And the way that you learn this delta, so this is the only math that you see. That is not true. There's another little piece of math later on, but the truth is that to learn this adversarial noise, usually we solve an optimization problem. And the way that we solve this, there are different ways, different attacks, but the gist is the same. So to train a neural network, we generally try to minimize the loss function. So minimization, if you've done calculus, is just you want to find where is the minimal value of the function that satisfies your constraint, right? So we want to minimize the loss function, which is the error that we might commit, okay? To create an adversarial image, we follow the same approach, but instead of finding weights for the classifier, we find the modification in the input space. So we found this perturbation that we need to add to the original image so that we end up with an adversarial vector, okay? And in general, there are a few things in computer vision that you have to think about. At least one is important, is the pixel perturbation according to a specific norm. In this case, just forget about norm. So how many pixels you can change, okay? There are different variants of this attack, but how many pixels you can change in the image, or you have to change the image to actually create a representation of this image that is adversarial, so that would cause a misclassification. And then also you want to minimize the loss of the target class, because you want the example to be misclassified as a gibbon, okay? Now, in this case, let's have a look at what happens in software, okay? Because in software, things are a little bit different. And then let's try to see whether we can draw some more generalizable takeaways. So in software, you can start off with an app, and for the sake of this, let's think about an Android application, okay? So you learn a suitable representation, and again, you can use a deep learning model, or you can identify a feature vector where each dimension in the vector represents something. For the sake of simplicity, let's say that we work with a manual engineered feature representation. So we have domain knowledge, and we say that each dimension in the vector represents an API that the application might execute. And we know this because we analyze statically the application. So we have a 1. We can represent this vector as a binary feature vector for simplicity. And we have a 1 if the API in that specific example is found, or a 0 if it's not found. Okay? It's a binary feature representation, very lightweight static analysis, very simple representation. And then we learn this adversarial manipulation. So how many of this 0 we need to turn to 1, and how many of this 1 we need to turn to 0 to create, by minimizing the loss function and the target class, to create a feature representation that breaks the classifier. There are a few nuances here, though. In this case, there's no visual representation that we need to satisfy. So before, you remember that we had to minimize the perturbation to preserve the semantics. So the image had to still be of a panda. I cannot just add too much noise, because otherwise the panda is not recognized as a panda anymore by humans. So the semantics has to be preserved. In the case of software, we don't have this. There's no concept of looking of the concept of the software, right? So perhaps there's no need to minimize the perturbation. This is a key point. Perhaps there's no need to minimize the perturbation, but we need to definitely still preserve semantics, like we've done for images. So we need to make sure that whatever perturbation we add doesn't modify the original semantics of the malware. If I have a malware, it still has to be a malware. So even more, if I have a malware, the perturbation has to translate back to code, and I have to be able still to compile the piece of software. Or if I work on binary, it has to be still able to run. And when it runs, it still have to be able to execute malicious functionalities. Otherwise, I create an adversarial vector that breaks the classifier, but it's not a threat, because the corresponding binary doesn't run, crashes, or it doesn't preserve the original semantics. Okay? And this is a key point. So instead of minimizing the perturbation, there are more generic constraints that we need to satisfy. We need to be able to preserve semantics. So we need to be able to make sure that the software runs as it was supposed to be running earlier. We need to make sure also that any modification that we add doesn't give away the fact that there's been some manipulation. Because otherwise, it's very easy to strip away these modifications and actually perceive this as no longer a threat. And again, here, the distinguishing point is the fact that for machine learning, this is still an attack. But if we don't satisfy these other constraints, it's no longer a threat. And when we reason about security, we reason about threat model. We reason about things that actually work and we care about. So here in software, there is something more challenging also, because whereas to create this adversarial example in computer vision, the technicality here is that the feature mapping function is invertible and differentiable, but just keep this jargon aside, meaning that I can create perturbations. I can go back to the image to change the pixel that I care about to create this adversarial image. In software, I have this blob, binary blob. I learn this representation, but then how do I go back to code? That's known as the inverse feature mapping problem, and this is a challenge. It really depends on what representation you learn and how can you go back. But this is another problem that we need to solve. Okay, so now this is the only complex slide probably that I wanted you to focus on. And if you are going to forget everything about what I said, but just remember this slide. So this is a fictional feature space representation. We have only two features, x1 and x2. So two features means that the vector that we use to represent a complex object has only two dimensions. In real life, we have, it depends on the representation, we have hundreds, thousands, or even millions of dimensions, okay? But of course, we can only represent things in 2D or 3D at most, but 2D is easier. So the red region is the region where all the malicious points lay. So this is a trained model. The blue region is the region in the feature space, so once we look at numbers, so these are vectors, so they just point in a space, okay? The blue region is the region where all the good points lay. And the arrows identify the direction of the gradient that I need to follow for turning one of the malicious points into one of the benign points. So gradient is just a fancy word to talk about differential, partial derivatives, because we have many dimensions. So think about derivatives, so because we want to minimize the loss function, as I mentioned earlier. But here we have more dimensions, so 2, 3, 4, 5, so we talk about gradient, but it's the same thing. Just think about one variable, it's just a derivative of the function. So in this region, we can identify a sub-region that is called the feature space visibility region. So these are all the points that exist in the feature space. We don't usually not necessarily know the shape of this region, but it exists. Within this region, we can identify what we call problem space visibility regions. So these are the regions that in which corresponds point that exist in real life. So here I can have, outside of this region, I can have a feature vector to represent a malicious point, but it doesn't compile, it doesn't run, it doesn't execute properly. In this region instead, in the problem space, I do have all the points whose representation corresponds to a real piece of software that runs, preserves malicious functionalities, and so forth and so on, okay? And the same for the goodware. Now, how does the attack work from an intuitive perspective? So we start off with a point that lays in the problem space visibility region. So we start from a program, piece of malware. We learn a representation, this vector. This vector belongs here because we know that that representation corresponds to a real program. Now, we run this optimization problem. We solve this optimization problem that I mentioned earlier, okay? There are different algorithms, different attacks that we can do, but the idea is actually by solving that optimization problem, I can modify some features in this vector. Do you remember the 0 that goes to 1, the 1 that goes to 0? So that this point is slowly, by following the gradient, so by following the minimal loss, the point goes somewhere in the region of the benign point. This is good because I created an adversarial example that now would break the classifier. So if I feed that representation to a classifier, the point will be misclassified as benign. The problem is that this point might not exist in real life. So it might correspond to a software that doesn't compile, that it might have not the malicious functionalities that I care about. So I need somehow to satisfy the constraints that we mentioned earlier. And this has the implication of sort of projecting that point back to one of the problem space visibility region. So I have to, by satisfying the constraint, I have to project the point back to where I have representation of point that exist in real life. So the corresponding adversarial examples now compiles, it executes, it preserves the semantics of the original malicious software, okay? So I have to do this because otherwise this is only a problem for the machine learning system, but it's not a threat anymore. I need to make sure that this actually represents still a threat nowadays. And if you think that this is only an academic exercise, I just mentioned one name, Silence, which is a real company that was actually broken because of this. Not because of the identification of adversarial example, but because the identification of realistic adversarial examples. Okay? So in doing so, there is some other term that appears here, that we call it eta, which is some other features that appear because of the fact that I had to satisfy constraints. So I had to constrain my adversarial manipulation in such a way to add maybe additional code to make sure that what I'm adding is realistic. And adding additional code might actually create new features that were not there at the beginning. They're not necessarily for the attack to be successful, but they're necessary for the attack to be realistic. Okay, and this is just the other maths part, but I just wanted to show you how the formulation of original adversarial machine learning attacks changed once we consider these more complex scenarios. And if you look more carefully about this is all mumbo jumbo, but it's very simple to understand. It just tells what are the transformations that we can do on the problem space, what are the constraints that we need to solve, and whether we can satisfy semantics, basically. And with this reformulation, we can also represent original adversarial examples in other domains, computer vision, for instance. In computer vision, some of these constraints are just satisfied by definition. You don't need to have them. So you may argue that this only applies to software. No, it's more generic. So this is just an example of an attack that some researcher performed on conference management systems. So their idea is to create a paper that was adversarial so that it would have been assigned to the reviewers that they wanted to select for this attack, okay? Because maybe they had colluding people, so they could actually do this. And here you still have to solve the same issues. So the no inverse feature mapping problem, meaning that once you find this adversarial representation, you need to go back to text. You can't just create some gibberish text. It has to be text with some meaning. And at the same time, doing so will create other features that you need to consider for the attack to be successful. This was published in 2023. And also, we explore the same issues in backdoor poisoning attacks, so about adversarial attack there. OK, enough chit-chat about the theory. Let's have a look about numbers. So this is an example of an end-to-end system Android realistic adversarial attacks that we performed against the state-of-the-art back in the 2020. So here you have our Android app that we impersonate as a real entity. Goes to a doctor, says, doctor, I have to make sure that I am perceived as a good application. Say, no problem, I can help with that. So the doctor says, I need to perform some and I want to notice also something that we carefully paid attention to, blurred out this part, So this was something that we really care about. So the doctor says, okay, no problem. So the technique that we use is called, from software engineering, is called software transplantation. You identify some piece of software, some piece of code in a software that you care about. It's like organs, so you just chop it out by using a technique known as program slicing. So you take out this part of code and you transplant it into another program. This is to make sure that we satisfy a few constraints. One of realistic, so we didn't really want to add orphan APIs or things that we care about in our adversarial example. We wanted to transplant something real that was part in the benign corpus of data. And we want to transplant it into the malicious software. To preserve semantics, to make sure that actually this new transplanted code doesn't interfere with the semantics, we actually wrapped this piece of code in what is known as an opaque predicate. Opaque predicate is just a fancy word for a conditional that is very hard to understand whether it's true or false at static time. So it's very hard, if you analyze it, it's very hard to understand whether it resolves to true or false. In our case, it always resolves to false, so that piece of code will never be executed. But it will be analyzed by our analysis system. Because it's a static analysis system, it will actually pick it up. And we want also to make sure that once you look at the code, you don't see anything dodgy. So it's a realistic piece of software, not just one API, but there's a complex program slicing that captures recursively all the complex objects that are used in the APIs. Okay? So if you're familiar with Android development systems, so you have intent, activities, they work with complex objects. So we do actually this recursive program analysis to make sure that what you have is realistic. Okay? So let me just skip a bit quickly on this part because it just tells some details on the program analysis. And I wanted to show you the attack, actually. So the system that we targeted, it's a very simple system. So the assumption is that the model for this work, but we can generalize. So the model is a linear classifier. So linear classifier means that it's very simple to interpret. You know exactly, once the model is trained, what are the features that are most responsible for benign classification or malicious classification. So imagine there is just a polynomial with the coefficients that are the weights of the classifier. So in this case, the attack starts off with a trained model. You pick up the feature with the greatest benign weight. We know it because it's highly interpretable, the model. We pick that up. We add that to our malicious point. So in that case, the 0 would go to 1 in this binary feature representation. We look actually in our database for the gadget, so this piece of code that corresponds to this feature. We wrap it up in an opaque predicate, and then we transplant it into the malicious piece of software. And then we do this basically for all the other features, basically. So then we go for the second most important benign feature, the third most important, and the fourth, and so forth and so on. And you can see that basically this has the effect of moving the points until it crosses the boundary between malicious and benign points. So at this point, we end up with a malicious point that crossed the boundary, meaning that it's in the representation of the benign point, but it's still a malicious program because we satisfy all the other constraints, so the semantics constraints. So if that program executes, and it behaves as a malicious point, but is misclassified as a benign point. So it's a little bit more complex than that because we have the side effect features, so the contribution of its gadgets, it's affected by the fact that you don't only have that feature, but you might have other features, the eta term, that actually is introduced because of our realistic attack. So that requires just to do some reordering of the gadget's importance and so forth and so on. So let's have a look at numbers, okay? So, and here I'm going to be going quite quickly. So data set, you read there, 170,000 applications, 10% of which are malware. I can argue on why 10% is malware, but let's take it as a fact for the time being. Classification, so two different classifiers, one linear SVM and another one that is actually a hardened version of a linear SVM that forces the classifier to basically use more features. So usually SVM as a classifier uses a few top features to make a classification. With SecSVM, the idea was to actually clamp the weights technically in the classification process so that you force the model to use more features. Why? Because the assumption was that the attacker had to minimize the perturbation. Remember at the very beginning with the computer vision example, he had to minimize the perturbation. And if I force the classifier to use more features, then there is a point after which I can harden the model. Because if you can't use more features and I force you to use more features as a defender, I'm actually having a robust model. But here we argue that you don't have to minimize because the game is different. So what is the effect into all of this? So the curve that I wanted you to have a look at maybe is the slowest growing curve. So this shows the attack success rate, so how good we are in breaking the classifier. In the most stringent settings, so on the hardened version for high confidence attacks. And you can see that by adding on average 120 features, including those needed for the attack, as well as the problem space, the side effect features, we are able to achieve 100% attack success rate. This is actually unsurprising because well, the assumptions are different. So the model requires you to minimize the perturbation, but we are arguing that you don't have to as long as you satisfy the other constraints. The real question here is, what are the effects of this manipulation on real-world statistics? So do you create binaries that are extremely larger than the normal binary size? Because if that happens, you're successful, but you give away there's something dodgy is happening. Turns out that we computed these statistics for a bunch of different metrics, and we can't see any statistical deviation from the distribution of these statistics with respect to the benign corpus of data, meaning that any adversarial manipulation that we induce creates adversarial binaries that run, execute the preserved semantics, and if you look at the statistics of sizes or cyclomatic complexity that tries to capture some software engineering properties, permissions, API calls, services, receivers, so a bunch of statistics of Android application, they look like, normal binaries. I mean, there's nothing odd that stands out for me. So the big question is, and this is the defensive part, this was only attack, right? So the defensive part is, as a defender, I can choose whether only generate feature space adversarial examples, so those that live in the feature space visibility region, because I'm a defender. I don't have to have something that runs. I just have to have something that hardens my model. But should I use that? Or should I use problem space adversarial example? See, because from an intuitive perspective, the thing seems to be fairly simple. The problem space visibility regions are the regions that identify points that matters. So in principle, you would like just to harden your model by exploring those regions. Because at the end of the day, if you're weak around outside of those regions, it doesn't really matter because the model is brittle, but at the same time, you don't have an attack. It's not a threat. But if you focus on the problem space regions, then those are the points that you should be defending from. But there's a cost in generating problem space adversarial attacks because you have to add the inverse feature mapping problem. So there's a real complex cost. So which one is? So this question actually was thrown last year in another top conference in academia. And these folks actually explored 3 different tasks. Text classification, so no LLMs. Text classification meaning sentiment analysis, positive or negative sentiment, okay? Text classification, botnet traffic problem, so network traffic analysis, and Windows malware. And they found that if you use problem space adversarial training, which is a technique to harden the model as you train the classifier, in text classification, you achieve 17% more robustness than using feature space attacks only for training the model. If you use botnet traffic, they're pretty much equivalent. And if you use Windows malware, then actually Windows malware really cares a lot about problem space adversarial examples for model hardening. So it seems that this is so basically, if we can summarize, for text classification is marginal, not required, required. So it seems that this is a task-dependent problem. I would argue that this is not a task-dependent problem. And I'll show you some number here. So we rerun our experiments and say, OK, now we have this adversarial, problem space adversarial examples. And then, can we harden our model? So it turns out that, it's a complex table. But actually, if you look at these numbers, you see that we have an order of magnitude more hardening if you use problem space adversarial example during the model robustness process. And this is the same here for the hardened model. So we actually go, so lower is better. So the attack success rate you want to see is basically 0 you want to see. So we tried this on different approaches too, and the problem is still open because what I argue is that this is not a task-dependent problem, but it depends on what I mentioned earlier, on the programmatized abstraction, the representation, the model you're using, and the attack that you're running. And this is an open research problem, and it's probably perhaps another story, okay? And for the time being, I wanted to thank you all. So, and I guess, research on problem space attacks and defenses is just the beginning, and I hope to have clarified a little bit that it goes beyond computer vision, and it can actually be a realistic threat. Thank you so much for your attention.
Thank you, Lorenzo, for the talk. Very interesting. And, this talk makes me feel that most people that talk about this stuff don't know much about it. And so you really showed that you know your stuff. Thank you.
Thanks.
In the interest of time, we have one question from the audience. Have you already experimented using a feedback-based technique which uses an LLM or AI to generate adversarial apps to model the perturbation?
Yes and no. So we are experimenting at the model at the moment on whether we can create malicious examples using LLMs, for instance. And there's a bunch of issues, of course, with jailbreaking, like safeguarding mechanism. But it's actually quite doable. What we've done, though, is this picture that I haven't had time. Oh, this has already gone away. But there was another approach where we are exploring reinforcement learning to actually create this game where we have a feedback loop system to create adversarial examples that are able to bypass adaptive defenses. So what we're trying to do is not to create attacks that break everything. We want to understand whether those attacks can be useful to harden our model, because that's the key point, and whether we should focus on that. Because we cannot explore the entire feature space. It's not possible. So if we can identify just pockets of regions where those are the things that matter, maybe we have a better option.
Thank you. And again, thank you, Lorenzo.